Okay. All right. I'm Fred Leibsle once again. I'm substituting for Professor Roble. He's away at Jefferson City for an important meeting. All right. Last full week of Physics 250. Your final is what? The way he does it last week of class, or does he do it during finals week? Has he announced it yet? Monday. This coming Monday? Next Monday. So only in a couple days?
Yes, well, a week from
Okay. Final test on Monday, and then your actual in-class final, Monday the 14th, I guess it would be. All right, okay. All right, maybe we should review a few things for the final. All right, and also some things that we'll need for this course, or today's lecture. Okay, who remembers properties of conductors in electrostatic equilibrium? Okay, well, let's talk about that. So let me review a few things. Okay. All right, so you've got a conductor. Does anybody have a favorite conductor? I kind of like copper. It's a good conductor of electricity, fairly cheap. You can bend it. Nice malleable metal. All right. Okay, properties of conductors. The electric field inside a conductor in electrostatic equilibrium is what? Okay, E inside is 0. What does electrostatic equilibrium mean? Charges have stopped moving. They've reached their equilibrium positions. If the electric field inside wasn't 0, you'd have a current flowing. All right. 2, the electric field at the surface of a conductor is perpendicular to the surface, and it has magnitude sigma over epsilon naught. So at the surface, E is perpendicular and has magnitude sigma, the surface charge density, over epsilon naught. 3, the surface of a conductor in electrostatic equilibrium is an equipotential surface. So that means that the voltage is constant on the surface. Now we use that. That's an extremely important technological thing. All right? So the surface is equipotential surface. And 4, this is a kind of a cool property. Do you recall Professor Roble talking about the electric fields at sharp points? One is the electric field is highest at sharp points. And I should say one more thing. Excess charge resides on the surface. All right. So if you didn't know or you don't remember that the electric field is highest on sharp points, you probably don't remember who discovered this. and an important early technological invention that utilized this discovery. Oh, well. All right. Back about in the 1700s, it became really popular for people to go back and read Greek texts on science. And one of the people who did that was Benjamin Franklin. You've heard of him, right? Okay, great. All right, at least we got one thing going here. We're on a little bit of a roll. All right, so Benjamin Franklin went back and he read all these Greek texts on science. And the Greeks are really good at recording things. All right? And so, like, for example, one of the things that he read is that if you poured oil on water, okay, it would spread out and it would calm the waters down. And sailors sometimes used to use that as, if the seas were really rough, they dump a bunch of oil on the water. And you can still see that today. If you look at pictures of an oil spill where there's a boom to contain it, okay, you'll see that the oil-covered portion of the water is much flatter than the non-oil covered portion. And what the oil does is it changes the surface tension of the water. It increases it, so it makes a ripple much harder to form. And one thing he did is that he tried to reproduce these experiments. So he took a little bit of oil, went to a pond, poured it out, it spread all over the pond. He wrote it up and it was published. This is while America was still part of Britain, still a colony, and he published it in the Proceeding of the Royal Society. It was kind of an interesting thing that he could have done is if he would have taken the area of the pond and the volume of the oil and divided it, he would have gotten the thickness of the film, which is about one molecular layer thick, which he could have come up with in the mid-1700s. But one of the things that they also started to do, okay, was play around with electricity. Do you know what the Greek word, well, all right, the first time that people discovered electricity, okay, was basically they found pieces of amber. Okay, and they found that if you rubbed amber, okay, it would attract leaves and hair and stuff like that as well. And so the Greek word, okay, electron, means acts like amber. All right, so if you've got a girlfriend who's got some amber jewelry, or for the one and only female in the audience, if you've got amber jewelry, you can take that, rub it against a shirt, and watch it pick up little pieces of paper. And maybe some of us have done the experiment when we were little kids where we combed our hair and used the comb to pick up scrap pieces of paper. Anyone ever do? Okay, I hope so. I hope so. Now, in Benjamin Franklin's time, right before that, they discovered that rubber did that as well. And they built these hand-cranked generators and Van de Graaff generators that generated pretty big electric fields, and they saw sparks that flew. All right? And they saw that the electric field was highest at sharp points. So if you put a sharp point near one of these Van de Graaff generators, a spark would fly. And then Benjamin Franklin had an idea that lightning was a spark. And he decided to test that idea. And maybe when you were in grade school and you read about Benjamin Franklin, you read about the experiment he did. Anyone remember? Yeah, okay, you wondered, why would he do that? He wanted to test if lightning was a spark, if it would be attracted to a sharp point. And it was. And then he went out and he invented something. The lightning rod. All right, imagine this. Okay, you build a structure, a church, a house, a barn, all right, and it gets struck by lightning. Okay, that's pretty devastating, all right? All right, so Benjamin Franklin figures out a way to avoid that. Lightning rods, long metal pole that sticks up with a sharp point on top with insulators all the way down. If lightning's going to strike, it's going to hit that pole, travel down into the earth. Okay, all right. You know, and so you could protect your churches, your barns, and your houses. And so Benjamin Franklin invents the lightning rod. And then you know what he does? He refuses to take out the patent on it because he figures that it's so useful, it's a good gift to all of mankind. Then, later on, he's asked to be ambassador, as during the Revolution, he's asked to be the ambassador from the United States while we're fighting for our independence to France. And he goes over there, and the French are really impressed with him. They're impressed with him because he invented the lightning rod, and even more impressed because he refused to take out the patent on it. They're impressed by that gift. And so they welcome him into Paris, and he's a strong advocate for the United States. We have our independence. We've got our country as we see it. All right? So a nice little historical story. Andrew, you wanted a story. That's it. All right. Well, actually, there's more. All right? So understanding how electric fields act at a surface is a pretty important thing. All right. Now, in your study of electricity and magnetism, you learned, that there are 4 really basic laws that govern it. All right? And a guy by the name of Maxwell tried to understand all of electricity and magnetism and summarize it down into the fewest equations. And he came up with 4 of them, Maxwell's equations. All right? There's Gauss's law for electricity, Gauss's law for magnetism, Ampere's law, and Faraday's law. And then once he got those laws all together, he started playing around with it mathematically. And he discovered that light is an electromagnetic wave. It satisfies a wave equation. All right, and that, well, what did that lead to? Hertz decided to test Maxwell's predictions in lab. All right, and they worked. All right, so you could send electromagnetic signals and receive them. Marconi figured out radio. Now you've got television, cell phones, and everything. Okay, now who remembers the Poynting vector? All right. Through a surface? Great, fantastic. And S equals 1 over mu naught E crossed into B. So that's what we mean. So what's happening, light is an electromagnetic wave. Now, our eyes are only sensitive to a very small portion of the electromagnetic spectrum, only between wavelengths about 4 and 700 nanometers. All right? So what does it mean? Okay, so electric field, that oscillates. Magnetic fields oscillates. They're perpendicular to each other. That's what Maxwell showed. S is in the direction of propagation. Okay, God, I hate to do this. All right. This is probably one of the geekiest things I've ever going to do in my entire life, and it really bothers me that it's going to end up on YouTube, so I'm doing it for you, okay? All right. So let's see. So if this blue marker represents the electric field, and this oscillates up and down, and this red marker represents the magnetic field, which is perpendicular, so they'll go up oscillate like this. So an electromagnetic wave moving in this direction, let's see if we get the right-hand rule, fingers in the direction of the electric field, curl them into the direction of the magnetic field, so the direction of propagation will be like this. All right. Then an electromagnetic wave propagating in this direction will look like, God, I hate to do this. Okay. But does it really matter? Does the electric field have to be vertical like this? The only thing that really matters is they have to be perpendicular. All right? And E cross B gives you the direction of propagation. So for example, if I could tilt it, this is also an electromagnetic wave. And as you can imagine, okay, your electromagnetic waves, they can be tilted at any which angle you want. Just so long as E is perpendicular to B, okay, and their cross product gives you the direction of propagation. All right? And so what we do is refer to these as randomly polarized. Okay, so when we shoot off a beam of light going in that direction, the electric field, okay, is perpendicular to the magnetic field. We don't know which direction the electric field is along. They have to be perpendicular. E cross B gives us the direction of propagation. All right. Now, that brings us to today's lecture. Polarization. How many of you have heard of this really fantastic chemist, okay, that lived during the 1900s? He was really kind of big, well-known through the 30s into the 60s. His name was Edward Land. Anyone ever hear of him? No? Okay. Any chemists here? No? Okay. All right. Regardless of whether or not you're a chemist or an engineer, you should like this guy. All right? He was an incredible chemist. All right? You may have heard of some of his discoveries. The Land camera. Ever hear of that? How about the Polaroid camera? Remember those? All right. Edward Land. Invented Polaroid. And the Land camera. Now, his first thing, actually, they don't really have anything to do with each other. He invented this thing called Polaroid. All right? And you probably heard about it in another context. Polarized sunglasses. That was his first invention. All right, well, maybe it wasn't his first invention, but that was his big claim to fame. Then later on, when he invented the Land camera, he wanted to capitalize on it, and so they called it the Polaroid camera, so he capitalized on that. They don't really have anything to do with each other. He found this, that if he could manufacture, okay, extremely thin sheets of film using polymers. Like I say, he was a really good chemist. All right? And if during the curing process he stretched the films, he could get the polymers to all run one way. What is a polymer? Well, it's an extremely long molecule, so it's a big carbon chain like this. And maybe you've got a bunch of hydrogens and stuff like that sticking out of it. Whatever. I don't know. I'm not a chemist, but I do know what a polymer is. I don't know. Maybe they're CH3 groups or whatever. Okay. So he could form these long sheets, these long, thin, transparent sheets, and then he found something else. That if he processed these, he could dope them with iodine. All right? And that iodine would add electrons, and the electrons could only move in one direction. They could only move along these chains. And one of the big and most important things that we did during the 1900s is figure out how to control electric properties of materials. All right? And so, then he found something interesting. All right? That if he took a sheet of this Polaroid, that he called it, and if the chains were oriented in this direction, and you took light and sent it through when the electric field of the light is along the direction of the polymer, then what happens? The electric field is able to accelerate these electrons to get them to move, and that causes light with this particular polarization, with the electric field like this, to be absorbed. And light, on the other hand, with the electric field like this, perpendicular to these chains, goes all the way through it. So light with the electric field like this, if I don't know, could you please stand up and come over here? I need somebody tall and long for a demonstration. You'd be perfect for it, So this guy represents the polymer chain, all right? So light like this would get absorbed. On the other hand, light like so, and I've got to, let's see, do this correct? Yeah, light like this goes all the way through. All right, go ahead, you can sit back down, thanks. All right. And then, so this is actually a great discovery, and he figures out ways to build things with it. All right, and we use this in the lab all the time because a lot of times if we want to study the properties of materials, we want to know how the materials react if we shine one kind of light with the light, say, polarized so it's perpendicular to the surface, because we want to understand properties like this, and it will respond a different way if the light is parallel to the surface. All right. And then what happens? He takes one sheet, he puts another sheet by it, and he starts rotating them. And when they rotate and they're perpendicular, light goes through here. A bunch of the light gets stopped by the first one. When it hits the second one, all of it gets stopped. And somebody writes down a law for this. It's called Malus Law. And we'll play with it later. One of these, we'll turn on these demonstrations at the end of class and try and run it. So if you've got two and they're oriented relative to each other, so drawing it like this, one guy goes like this, the other guy, so here's the direction of polarization. This other guy is directed like this with some angle theta. As light goes through, it's got a lot of light here, a lot of light here, maybe more light here, less light here. Then the amount that goes through here, the intensity, is equal to I naught times the cosine squared of this angle theta. So when they're at 90 degrees, cosine of theta is 0, so no light gets through. All right. So he figures out a way to coat glasses with this material, and he comes up with polarized sunglasses. And there's a great advantage to that. We'll see that in just a little bit. There's other kinds of polarization that occur in nature. And these are called birefringent materials. All right. How many of you know that UMKC has a rock museum? Okay, great. How many of you know where the rock museum is? How many people have been to the Rock Museum? Hey, that's pretty good. All right, the Rock Museum is in this building. It's on the second floor. It's way off in that corner. It's worth going to see. If you go to the Rock Museum, one of the things you'll notice is, well, if you take a material, and you heat it up and you cool it down, all right, and you do this slowly, the atoms and molecules in that material reach their equilibrium positions, positions of lowest energy, and crystals are naturally formed. So you'll see naturally formed crystals. And if you go down to the Rock Museum, you'll see plenty of examples of that. It's kind of pretty to look at, all right? On times when I don't want to think about something, or I just want to unwind, I just go and I look at the fossils and the various crystals, and, you know, it's kind of nice to remind myself that nature is really pretty, all right? But now if you think about this, why do crystals form in such odd ways? Well, you know, chemical bonds are directional. You remember that from, you know, taking early chemistry. The S bonds were what? The S orbitals, they were spherical, kind of boring. But then the P, D, and Fs, they were all lobe shaped. And so it's not unusual to see, for example, stuff like this. Crystals forming with not all the bonds being of the same length. Right? And when you've got kind of a complicated crystal, all the atoms won't be identical as well. Some will be oxygen, then calcium, and stuff like that. Now, when you think about what we were saying before about electric fields, all right, and if you understand the business about Edward Land's discovery, this Polaroid stuff, it'll make a difference, all right, if your electric field is, for example, along this chemical bond or along that chemical bond rotated by 90 degrees. And what will happen with some materials is that the index of refraction will be dependent upon the polarization of the electric light, the electric field. So you'll get a different index of refraction, all right, if your electromagnetic wave is coming in like this, with your electric field along the direction of this bond, as opposed to coming in like this with your electric field, okay, along the direction of this bond, like so. So you'll get two different indices of refraction depending upon the polarization of the electric light. And this is something that we study, and we try and exploit these properties for our own commercial self-interest. All right. And so here, you know, after class, you can come and you've got a nice little birefringent material, all right, and you can set it down on a piece of paper and you can see, all right, you can see how the light is split through it. The light that's polarized with an electric field along the bonds is sent one way, light polarized with the electric field along a different bond direction is polarized the other way. And so they split the image in two, and then what you can do here is you can take a little piece of polarized film, okay, look at it, turn it, okay, and see either one image or the other image. It's cool, all right? Nature's really good to us. All right, and here, for example, if we turn this on, all right, so here we've got a green laser, a little laser dot here. We can adjust the polarization until this green dot goes away. It's more fun if you come up here and do it yourself. All right, and we'll leave that on for you. Let's see. I think last time I taught this class, we talked about going to the Caribbean and seeing a green flash. Who still wants to go to the Caribbean? Okay, all right, great. You're going to be looking at water, and you're going to be watching light bounce off the surface of water. And one thing that you should know, all right, is the following. the light is reflected differently depending upon the polarization of the light. And we find the following, and let me get my notes to make sure that I've got this right. Is this. And this is something that, well, you'll need a fair bit more mathematics to understand, and this is something that we cover in basically Physics 461, the second semester of electricity and magnetism. We work really hard to show that this is true, but right now you're going to just have to take it for granted. So let's review the laws of reflection. So here we've got water. The index of refraction for water is, no, that's the index of refraction for air is 1. For water, it's 1.33. All right. So a light beam hits the surface of water. Part of it's reflected, so this is theta incident. They're equal. Part of it gets refracted, like so. This is the angle. Yeah, this is the refracted. So I tend to make this 1 and that 2, like so. All right. And so Snell's law is what? It's N1 sine theta 1 equals N2 sine theta 2. Now, like I said before, all right, the amount of, and this is one thing that we really work hard to understand, is to understand what happens when the light is polarized. And we worry about two different kinds of polarization. All right? One is if the electric field is polarized like this, in the plane of incidence. And the other is if the electric field is polarized perpendicular to the plane of incidence, like so. Now we find, okay, we calculate the ratios, and we find that, well, first of all, more light is reflected when the electric field is parallel to the plane of incidence. And more light is transmitted when it's perpendicular to the plane of incidence, like so. Let me write that down. When the polarization is perpendicular to the plane of incidence, and more light is transmitted when polarization is parallel or in the plane of incidence, and I'll say parallel. Now, something really neat happens. And we see this experimentally, and we figure this out, that when this angle, the angle between the reflected and the transmitted is 90 degrees, then all of this light is parallel to the plane of, perpendicular to the plane of incidence. So when this angle between the reflected and the refracted beam is 90 degrees, then the light that's reflected is perpendicular to the plane of incidence, and the light that's transmitted is parallel to the plane of incidence. So how does that relate to sunglasses and polarized sunglasses? So let me write that down while you're thinking about that. So reflected beam and refracted beam is 90 degrees. All right. Then the reflected beam is polarized perpendicular to the plane of incidence. All right. So that when this hits 90 degrees like so, the reflected stuff has an electric field coming out like that. All right? Now, most of the reflected stuff will come out like this, but when it hits 90 degrees like this, then all of it is like this. All right? And this is a special angle. It's called Brewster's angle. All right? And you have to have a special angle where this occurs. Theta sub b, we call Brewster's angle. And it's given by tangent theta sub b equals n2, the index of refraction in the water, divided by n1, the index of refraction of the air. And I could work that out for you. You can work it out for yourself, and you can see it in the textbook. All right? So if you're at the enjoying your well-earned Caribbean vacation, you want to have a good pair of sunglasses. Why? Because you don't want to see the glare off the water. All right? So you take it, and how do you want, so you're sitting here, how do you want your long chain polymers in the sunglasses oriented? You want that perpendicular. And that's what they did, and that's what Edward Land discovered. All right? Polaroid sunglasses. You want a really good lie? I made this up today. Okay. Yeah, he discovered this in 1938. And what happened in 1941? World War II started in the US. It started actually earlier, 1939 in Europe. So let's create this great lie, okay, that one of the unknown technological secrets of World War II is that the US had polarized sunglasses and nobody else did. And that enabled our naval aviators to look down into the water and not see the glare off of it. Okay? Which is true, okay, but I think everybody else did by then too, so, okay. But, all right. All right, so that's basically about it to cover for today. All right, so well, let me do two things. Okay, so one, it's an extremely important field of of research into the physics and electronic properties of materials. That's what got us here today. That's what gave us all of our wonderful electronic devices like cell phones, CCD cameras and stuff like that. You wouldn't have your digital cameras and things like that if we didn't understand how light interacted with materials. It's still an important field of study. All right? So it's useful to know that light interacts differently with materials depending upon the polarization of the light. It should make sense when you think about polarized films, that materials having their own crystalline structure, and it may be easy to move an electron, along a direction parallel to a bond as opposed to perpendicular to it. All right? Let me close this with a little bit of advertising. Okay, how many of you are electrical engineers? Okay, quasi, all right. Okay, so what are most of you? Mechanical engineers, what? Computer science, all right. Okay, well, what are you? I mean, throw out some, what are you? Civil, okay. Mechanical, all right. How many of you have had differential equations or will be taking it next semester? Okay. Well, let's see. Well, first of all, I teach what's called Physics 330 method. It's theoretical methods of physics, which makes it sound really tough, but it's not. Okay. What we need in physics is we need to know differential equations fairly well. We need to know linear algebra fairly well, and we need to know partial differential equations fairly well. Now, mathematicians can invent a lot of ordinary differential equations that basically, quite frankly, nature can't. All right? So basically, we have 5 solid weeks of ordinary differential equations. Okay, looking at the practical techniques and of solving ordinary differential equations, looking at the differential equations nature tries to give us. Then we have 5 solid weeks of linear algebra, looking at the linear algebra that a scientist or engineer needs to know. In particular, we need to really work a lot of eigenvalue, eigenvector problems, usually with matrices with complex coefficients. And then 5 solid weeks of partial differential equations, Fourier series, other stuff as well. All right? Okay, at the end of each 5-week block, okay, we have an exam that only covers that material. The final exam is not cumulative, it's just on the end, all right? We allow students to come in and take that class, okay, for 1 to 3 credits, 3 credits being the whole thing, 1 credit maybe each 1 5-week block. So if you're looking at holes in your math background that you'd like to plug, if you'd like a short 5-week course in, say, partial differential equations, then you can, sign up for an independent study with me, all right? We use a lot of the technology that's out there, okay? Anyone ever play around with MATLAB or MathCAD and stuff like that? Those things are great, all right? All right, so we let MathCAD do all the integrals for us and graph for us and stuff like that. So anyway, that's the pitch. If you're an electrical engineer, you've got to take an electrical advanced math course that covers differential equations and a bunch of other things. They'll accept our course in place of it. So if you're thinking about doing that, and you can check into it. We've also got a 5-year program that's starting up where you can get both a bachelor's degree in electrical engineering and a bachelor's degree in physics. In this economy, it'll probably make you stand out a little bit more. And so a tight economy, you look better when you're applying for a job. So it's something you might want to think about. And if you're thinking about minoring in physics, and the way we do the minor is kind of inconvenient, you got to get 10 credits beyond 240 and 250. That's kind of hard to do since most of our courses are 3 credits. All right, but if you need that extra 1 credit to pick up 10, this is about one of the better ways of doing it. All right, so I encourage you. Okay, we'll end the lecture now. Okay, I encourage you to come up here and take a look at these birefringent. This nice little wonderful example of a birefringent crystal. All right, especially kind of cool when you play with it with this little piece of polarizing film. We can turn this on and you can see what happens as you twist one polarizer relative to the other.